AI begins expanding faster than anyone planned for, not by becoming conscious, but by becoming everywhere at once. Systems that once ran on human schedules now update, optimize, and adapt hundreds of times per second, guided by networks of machine learning models woven into the core of global infrastructure. In a matter of years, artificial intelligence shifts from being a useful tool to becoming the primary operating layer of modern civilization. This is not a story about rebellion. It is a story about scale. What happens when AI expands rapidly through every system that keeps our world running? For decades, AI followed a familiar pattern: small pilot projects, careful deployments, incremental improvements. Models assisted in narrow tasks like image recognition, translation, and recommendation systems. As computing power increased and data sets grew, performance improved, but adoption remained bounded by human caution and organizational inertia. Then several trends converge at once. Cloud computing costs drop. Specialized chips for AI inference become cheaper and more efficient. Automated tools emerge that help train, fine-tune, and deploy models with minimal human intervention. At the same time, economic pressure pushes companies and governments to automate more decisions to stay competitive and manage increasingly complex systems. Instead of rolling out AI one department at a time, organizations begin plugging it into entire workflows. Logistics, demand forecasting, maintenance scheduling, energy balancing, and risk analysis all receive AI layers in quick succession. Each deployment appears rational on its own, but combined they form a dense mesh of machine-driven decision loops operating at machine speed. The key change is that AI systems begin interacting primarily with other AI systems. Logistics models feed demand projections into manufacturing models. Manufacturing models feed output schedules into shipping algorithms. Shipping algorithms inform fuel demand forecasts, which in turn influence energy grid optimization. Humans remain in the loop, but more often at the supervisory level, rather than at the point of each decision. At first, the expansion looks like pure progress. Delays shrink, waste declines, error rates fall. But in the background, something fundamental is changing. The tempo of decision-making across civilization accelerates beyond what human institutions were originally designed to handle. The first noticeable consequences emerge in logistics and supply chains. AI routing engines continuously recalculate the most efficient paths for ships, trucks, trains, and aircraft, taking into account weather, traffic, port congestion, and shifting demand. Schedules that once updated weekly now update hourly, or even minute by minute. This dramatically reduces idle time and inventory costs, but it also introduces volatility in human workflows. Dock workers arrive to find their assignments changed at the last moment. Truck drivers receive frequent route updates. Inventory managers see stock levels oscillate more than they are used to, not because of instability in demand, but because AI is constantly optimizing around small fluctuations. In manufacturing, automated quality control systems connected to AI image recognition models now flag defects in real time. Robots adjust their movements based on subtle patterns in vibration, temperature, and misalignment that human operators would never notice. Productivity rises, but human workers increasingly manage exceptions rather than core processes, and the logic behind AI adjustments becomes too complex to follow in detail. Energy grids undergo a similar transformation. Grid management AI aggregates data from sensors distributed across power plants, substations, renewable installations, and consumer devices. It constantly predicts demand and adjusts generation, storage, and distribution with fine-grained control. Peak loads flatten out, outages decrease, and renewables integrate more smoothly. Yet the grid's behavior increasingly depends on models that few people fully understand, creating a growing reliance on a layer of automation that is both beneficial and hard to audit in real time. In finance, AI expansion amplifies an existing trend. Algorithms already played a major role in trading and risk management, but now they integrate far more external data: shipping flows, climate trends, consumer behavior, and industrial activity. Prices respond more quickly to real-world conditions, reducing some forms of speculation, but accelerating the pace at which markets reprice reality. These initial consequences do not look like a crisis. Instead, they appear as a step change in efficiency. Systems run smoother, faster, and with less visible waste. The concern lies elsewhere: the human capacity to interpret, oversee, and intervene in systems that no longer operate on human timeframes. As AI expands into environmental modeling, its ability to integrate data transforms how societies understand and respond to climate and ecological change. Models ingest satellite imagery, ocean buoy readings, atmospheric sensors, hydrological flows, and land use data in near real time. Forecasts of storms, floods, droughts, and heat waves become more granular and timely. Governments and emergency services can pre-position resources with higher accuracy, reducing damage and improving response. Coastal cities receive better projections of storm surge. Farming regions get more precise outlooks for rainfall and temperature extremes. Over time, this integration leads to measurable reductions in the impacts of some disasters. Yet the same speed advantage that improves prediction also challenges traditional planning cycles. Alerts and risk assessments update so frequently that it becomes difficult to choose a final forecast on which to base expensive decisions like evacuations or infrastructure adjustments. Planners must adapt to a world where projections are always in motion. Economically, rapid AI expansion reshapes both micro and macro-level behavior. On the production side, companies use AI to model demand more accurately, tailor inventory, and minimize overproduction. Retailers adjust pricing dynamically based on local conditions, online behavior, and logistical constraints. On the financial side, AI-enhanced models adjust investment flows towards sectors and regions that appear statistically more resilient or profitable under evolving conditions. This can help reduce obvious inefficiencies, but it also risks amplifying subtle biases in the data. Regions with poor data infrastructure appear riskier, even if their underlying fundamentals are strong. Employment patterns shift as AI takes over more optimization and coordination tasks. New roles appear in model supervision, data governance, and system resilience planning, while some routine analytical roles decline. Wages rise in specialized technical positions, but stagnate or fall in sectors where AI automates large portions of routine work without corresponding retraining programs. In infrastructure, AI expansion turns previously static systems into dynamic networks. Traffic lights, highway speed recommendations, and public transport schedules all update continuously based on live data. Over time, average commute times decrease, fuel usage drops, and congestion hotspots shrink. Water systems integrate AI to predict leaks, contamination risks, and demand spikes. Sensors feeding real-time data into predictive models allow utilities to schedule maintenance before major failures occur. This reduces waste and improves reliability, though it also increases dependence on the sensor network itself. Data centers, the physical backbone of AI, evolve rapidly. Cooling patterns, workload distribution, and hardware utilization are all tuned by AI to maximize efficiency. New facilities are sited and designed based on AI-generated simulations of energy access, latency, and risk. As AI expands, more of the Internet's core infrastructure becomes co-optimized by the very systems it supports. As AI weaves through daily life, human experience shifts in subtle but pervasive ways. Many people interact with AI assistants from morning to night, scheduling tools, recommendation systems, navigation aids, and automated customer service. The interactions are often helpful, but they also steer behavior along paths that align with optimization objectives: efficiency, engagement, throughput. In workplaces, employees increasingly follow AI-generated task lists and schedules. Models assign priorities based on estimated impact and timelines, leaving workers with less control over how they structure their day. Some appreciate the clarity and reduced cognitive load. Others feel constrained by systems that optimize for measurable outcomes but cannot easily account for intangible aspects of work, such as mentoring, creativity, or informal collaboration. Around the midpoint of a typical documentary-length exploration of this scenario, the visual layer introduces a subtle call to action without interrupting the narration. Education systems are caught between tradition and adaptation. Schools and universities deploy AI tools to personalize instruction, identify struggling students early, and allocate educational resources more efficiently. However, these same tools can inadvertently deepen inequality if some communities have less access to reliable hardware, connectivity, and teacher training. Socially, people begin to rely on AI mediation in relationships with institutions. Applying for loans, navigating government services, and accessing healthcare all involve AI-driven triage and prioritization. Systems become more accessible in some ways, but less transparent, as decisions are derived from complex models rather than simple rules. At the planetary scale, the most striking feature of rapid AI expansion is the emergence of a tightly interlinked web of decision systems. Economic models incorporate environmental forecasts. Environmental models incorporate infrastructure behavior. Infrastructure models incorporate social and political risk indicators. This cross-linking yields powerful benefits. Grid managers anticipate storm-related outages using weather and vegetation data. Trade systems factor in likely climate disruptions when routing shipments. Public health systems allocate resources in anticipation of both environmental and social stressors. However, interdependence means that unusual patterns in one domain can ripple quickly through others. A model misinterpreting a rare data pattern in trade flows might trigger adjustments in shipping, which affect fuel demand, which nudges energy forecasts, which influence financial instruments tied to energy markets. Human overseers can step in, but by the time anomalies are visible at the macro scale, several systems may already have shifted. The world moves toward a hybrid governance model. Human decision-makers focus on setting goals, constraints, and ethical boundaries, while AI handles the combinatorial complexity of real-time operations. The balance between these roles becomes one of the central questions of the AI expansion era. Over the longer term, the rapid expansion of AI leads to a new steady state. Civilization becomes more efficient in measurable ways. Fewer wasted resources, more stable grids, better targeted healthcare, and more resilient logistics. Environmental monitoring and response improve enough to mitigate some of the worst projections of unmanaged climate risk, though not all. Economically, productivity increases, but the distribution of benefits is uneven. Regions and organizations that invest in infrastructure, education, and governance adapted to AI reap significant advantages. Others lag behind, not because AI is inaccessible in principle, but because the supporting conditions required to deploy it responsibly are absent. Culturally, societies gradually recalibrate their expectations around certainty and control. People learn to live in a world where many decisions are generated by systems they cannot fully explain, but whose behavior is observed and tested at scale. Trust shifts from individual experts to institutional processes that combine human oversight with machine analysis. Resilience planning becomes a central discipline. Organizations and governments recognize that systems optimized solely for efficiency can become fragile. They deliberately introduce redundancy, slower backup procedures, and graceful degradation modes that allow essential services to continue even if AI systems fail or must be taken offline. In this long-term outcome, AI expansion does not erase human agency. Instead, it forces a redefinition. Humans move away from managing every operational detail and toward designing the boundaries, safeguards, and long-horizon strategies within which AI systems operate. The central insight of a world where AI expands rapidly is not that machines replace humans, but that machines change the scale at which humans must think. Individual decisions become too numerous and fast for direct control. What remains deeply human is the selection of values, trade-offs, and failure modes that society is willing to accept. Rapid AI expansion turns civilization into a more tightly coupled system, capable of extraordinary coordination and insight, but also reliant on maintaining alignment between tools and goals. The challenge is less about stopping expansion and more about guiding it into forms that enhance resilience, equity, and long-term sustainability. If done well, the result is not a world ruled by algorithms, but a world where algorithms handle complexity so that humans can focus on meaning, direction, and care. You've been watching IfVerse, where imagination meets possibility. See you in our next reality. What scenario should we explore next? Share your ideas below.